Alright, we're here with nomenclature, naming. In this case, we're going to name ionic compounds. So in ionic compounds, when you have a positive thing and a negative thing bonded together because their opposite charges help them hold together. So our learning target is if you have the ionic name, you can go to the formula, or if you have the formula, you can go to the name. We'll do some example problems here. But first, there's some rules to look at. I would get these down in your notes. Remember, you're always going to give the cation, the positive thing first. So that's going to be your metals. Everything to the left of your staircase, everything over here to the left of the staircase, all your metals, those get named first. Then the anion, the negative thing, second. The cation name is just going to be whatever's on the periodic table. So just magnesium, just cesium, just lithium, just aluminum. No change to it. The anions, which are up here in the top right of your periodic table, those are your anions, your negatively charged elements. They are going to change their ending to "ide." So if you think of this like a man and woman getting married, if we make the metals be our men and the women be non-metals, usually when a man and woman get married, often the woman changes the end of her name. So in the same way, the non-metals are going to change their ending. In this case, from sulfur to sulfide, and oxygen to oxide. So all non-metals get an "ide" ending when they're in an ionic compound. That's the name of it. Okay, so let's practice some of these. Now note there are some subscripts here. There's 2 in Na2S, and the 2 and 3 in Al2N3. We're not going to worry about those yet. They'll come into play later, but we're not there yet. They're not important at the moment. So Na2S. First thing is our cation. That's just the metal, Na, which is sodium. So we'll put down sodium. Our non-metal, our anion, is sulfur. So it would be sodium sulfur, but it's an anion, and all the anions change the ending of their name. So we go from sulfur to sulfide, for a total name of sodium sulfide. Cool. Okay, then we've got calcium as our metal, Ca. That's our cation, so it's going to be calcium. Our non-metal is oxygen, but oxygen has to change its ending also to calcium oxide. And our last one, aluminum, is also a metal, so Al becomes just aluminum over here. And it'll be nitrogen. Nitrogen changes ending from nitrogen to nitride. Some people might try and do nitrenide, but it sounds funny when you say it. You probably have the syllables off a little bit. Just tweak it till it sounds more fluid. Okay, that's going one way. So that's when we have the formula, we're trying to get the name. Now we have the names, we need to get the formulas. This word makes it a little trickier. We have to both take the name of magnesium oxide, find out what elements they're talking about, discover their charges, and then put them together so there's no leftover charge. So we have to take magnesium and oxygen. Because magnesium is our cation. Its most common charge would be 2+, needs to lose 2 electrons to get back to that noble gas configuration where it's most stable. And oxygen has to do the exact opposite. It's got to gain 2 electrons to get from, let's see if I can do this. Oxygen's here. It's got to gain 2 electrons to get to be like neon, to get to be like the noble gas. It gains 2 negative things, becomes O2-, Mg becomes 2+. Once we have the charges, we're going to put them together, and if we look, we need to do this until we have an equal number of charge. So our 2+ and our 2-, those add together to make 0. Our charges are even, they cancel out, so it's neutral, and we get MgO. That's your formula for magnesium oxide. Cool. It's nice and easy like that if it's an even charge on both sides. It's not always going to be that way. If we look at aluminum fluoride, we get charges on aluminum of Al3+, and a charge on fluorine of 1-. So we take these and put them out here. We've got a 3+ and a 1-. Those are not even. If we said the formula is AlF, it'd be like we go on and grab onto something and we'd be getting electrocuted because we've got 2 extra positives on the aluminum compared to the fluorines when they add up. right? 1 minus and 3 plus adds to 2 positives. We'd literally be being electrocuted if that's what the formula was. So that can't be right. We need to look at which one we need more of. Do we need more positive charges or more negative charges? Well, we've got 3 positives and only 1 negative, so we need to add in more negative charges. We can't just make F 2 minus though. F has to be a 1 minus charge, but we can add another F 1 minus in here. So now we've got fluorine, 2 of them, with a 2 minus charge total. So there's 2 negatives, 3 positives. Closer, but we're still short negatives, so we'll add in another F minus. Now there's 3 negatives total, 3 positives total, so our positive charges and our negative charges cancel out and add together to make our formula of AlF3. That is aluminum fluoride's formula. Next one is strontium nitride. So we need to get the charges for each of those. So strontium is 2 plus, nitride is 3 minus. When we put them together, those don't add up to 0 either. We've got more negatives than we do positives right now, so we need to add more of our positive thing in there. So if we add more strontium in there, cool. We now have 4 pluses and 3 minuses. Still not even. Now we're short on our negative side, so we add in more negatives by adding another nitrogen in there, technically a nitride ion. We now have 6 negative ions and 4 positive. So still not even. Now we're short on the positive side, so we'll add another of our positive ion in there. So we now have 3 strontium, 2 pluses, and 2 nitride 3 minuses. So 6 negatives, 6 positives. Those are even. Those will cancel out. So we combine it to say we've got a formula of SR3 because it took 3 SR atoms, and 2 nitrogens. There are 2 nitrogens here. The charge won't matter because in the end it cancels out. So there's 3 strontiums denoted by this 3, 2 nitrogens denoted by this 2. So SR3 and 2 is strontium nitride's formula. Alright, let's look at our last one. Lithium phosphide. So we got our charges of Li1 plus and phosphide's charge of being P3 minus. We put them together, those are also not even. We have 3 negatives and only 1 positive. So we definitely need more positive charges to make this work. So we need to add in more of our positive ions. So we need more lithium pluses. That gives us 2 pluses and 3 minuses. We need to get 3 pluses and 3 minuses. Now that they're even, they'll add together to get a charge of 0, and our final formula of Li3, whoop, that's a typo, should be Li3P. So ignore the fact there's an N here. It should be Li3P as our final formula. Typo on my part. Okay, so that's going from name to formula. That's our first type. There's a second type of ionic naming called polyatomic ion naming rules. Atomic just stands for atoms. Poly, the prefix poly, means more than one or multiple. So we mean multiple atoms naming using ionic rules. So in this case, the rules are still going to be we put the anion or positive thing first, then the cation or negative thing second. That has not changed. Our metal name comes from the periodic table. Now we're going to get names of polyatomic ions. So these are usually negative, but not always. There's 1 or 2 positive ones out there. So when we name the first set, oxygen would go to oxide, nitrogen would go to nitride. These polyatomic ions, their endings do not change ever. And the formulas for the polyatomic ions don't change. So if it's like P2O3, you can't go changing the little subscripts on there. They're a group. They're like a band. If you were to try and double or triple the number of singers in a band, it's not going to work. You wanted the same song or same noise, same music. You got to keep the band the way it is. You could have a second band or a third band, but you can't just add in random members to the band. Okay, so first, to make sure this works, you have to recognize that there is a polyatomic ion. The easiest way to do this is to notice that there's more more than 2 capital letters in your formula, or from the end of the name. We'll point that out when we go through some examples. If you're in my class, I give you a list on the back. Here's our periodic table. If you look on the back, there's stuff in this black box. It says -1, -2, -3, +1. These are all your polyatomic ions. So I'm giving them to you. You don't have to memorize them. You have to recognize that it is a polyatomic ion to look there and use those for those names. Then our next step, if you're adding those subscripts, like if you're having more than one band, you need to protect the polyatomic by putting parentheses around it and putting the subscript down below outside the periodic table, outside the parentheses. So example, MgNO32. We know it's a polyatomic in here because we've got one capital letter at the M, a second one at the N, and a third one with the O. If there's more than 2, we know it's a polyatomic ion in there. And since we need 2 of this NO3 group, we protect that group by putting in parentheses, then putting a 2 outside, saying we need 2 of this entire group. So if we just put a 2 without the parenthesis there, it'd be like we have 32 oxygens, which would be significantly different than having 2 of the entire group. Or NaOH. This one doesn't need parentheses because there's only one OH group, but it's still a polyatomic because we've got 1, 2, 3 capital letters. Now note, the ending here, magnesium nitrate, that nitrate group you'll find right on the back of the periodic table in that chart. Same thing with the OH group, it's called a hydroxide group, you'll find that back there as well. Alright, let's practice some of these. Now again, when we're going from formula to name, you don't have to worry about the subscripts again. We don't care how many of these little numbers there are outside of the parentheses. Inside the parentheses, it does matter. Okay, first one, the first thing we have is going to be our cation. So it's going to be CsBrO. So Cs is going to be on the front of the periodic table. It's a metal. It's cesium. So cesium, then we have to find the BrO group on the back of the periodic table. So find it on the back in your chart here. And you put them together, you'll find out that it's going to be cesium hypobromite is the name of the BrO group. Next one's Mg3PO42. We don't care about the 3 here or the 2 here, but this PO4 is a whole group, so we do care. So it's going to be magnesium. Then on the back periodic table, that PO4 group is called phosphate. So the whole thing is magnesium phosphate. Last one, in parentheses, this is a positive polyatomic. It's out in front. So this NH4 group on the back is called ammonium. And then we have sulfur. But sulfur at the end does change its name. So this one's going to be ammonium sulfide as its ending. Okay, now we go the other way, getting our charges correct. Okay, so cesium acetate. I get cesium's charge and acetate's charge. Acetate, the charge is given to us on the back when we find that group. We know most of these are on the back because if it ends in ate or ite, ATE or ITE, it's probably a polyatomic. You should look on the back of your periodic table. 1 plus here, 1 minus here, which means we only need 1 of each. And we'll end up getting CsC2H3O2. Boron nitrate, we've got 3 plus, and this nitrate group, NO3, has got a 1 minus charge. These are not even, so we need more of our nitrate. 2 minus, 3 minus, and 3 plus. Now it's even. Here's our final formula, BNO33. We need the parentheses, we have 3 of this entire group here. Same thing for ammonium sulfide. 1 plus here, 2 minus here, so we need 1 more positive charge. Now there's 2 positives, 2 minuses. For NH4, 2s. And our last one's magnesium phosphite. 2 plus on magnesium, 3 minus on phosphite. So when we put them together, we need to have a more positive to start with, so we add more magnesium. Oop, that's on top of itself. Another phosphite. Now we got 6 negatives, only 4 positives, so add 1 more magnesium in there. Total of, now we got 6 plus, Sorry, it's messy. And 6 minus, so they add together to get our final thing of Mg3PO3 2.